AP Calculus AB, section 3.9, page 4. And today we are going to be talking about logarithmic differentiation. We've really done two types of derivatives so far this year. We've done things like this. F of x equals x to the 8th. And when you do the derivative, f prime is 8x to the 7th. So we had a situation that was set up as a variable raised to a constant exponent. Then we just spent a day or two looking at things like this. F of x equals 8 to the x. And doing that derivative, we had, this was an a to the u, so 8 to the x times the natural log of 8 times the derivative of the u, 1. And this situation was a constant raised to a variable power. Oops, gotta turn my paper. Constant raised to a variable. All right, logarithmic differentiation is used when the function is a variable raised to a variable power. So an x to the x, oh, like this one, or down here, cosine x to the x. Or sometimes logarithmic differentiation can be used to avoid very messy product rule, quotient rule combinations. All right, let's start doing this derivative. And at the same time that I actually take you through this process of logarithmic differentiation, I'm going to iron out what the steps are for you so that you can do this later, because there's quite a few steps to do. All right, the first thing that we're going to do is to take the natural log of both sides. So we'll take the natural log of both sides here, and we'll have the natural log of y equals the natural log of x to the x. The next thing then that we're going to do is we're going to rewrite using the log rules. In this case, we're going to take this exponent and pull it down in front. And that will give us ln(y) equals x ln x. Now be careful, we've not done a derivative. You're thinking it's the same thing of pulling that x down in front, but we're not doing a derivative here. We are just doing the log rules. Now let's differentiate both sides. And the derivative of a natural log y, that's like f of x in here, don't forget. So that's 1 over the y times the derivative of the y, dy dx, equals, and on this right hand side, we have a product rule going on. So first, times the derivative of the second, 1 over x, plus the second, ln x, times the derivative of the first, which is a 1. Then simplify, and this left side, 1 over y, dy dx equals on the right side, x times 1 over x, that's 1, plus a natural log x. The next thing then is to solve for dy dx. And in this case, I'm just going to multiply by y. Dy dx equals y times 1 plus the natural log of x. And very last then, sub back for the y. All All right, so where were we? What was y initially? Oh, y was x to the x. So we'll sub right back for that. dy dx is x to the x times a 1 plus the natural log of x. There's the derivative. All right, let's go down here and let's take a look at this one. Now, you won't be able to see my steps at the same time as I'm working through this problem, but you have the steps right up there. You can see as we go through. All right, first step is to take the natural log of both sides. So we'll have lny equals the natural log of cosine x to the x. Then let's rewrite using those log rules. lny, and again, we're going to take this exponent up here and we're going to leap it down in front. X ln cosine x. Now differentiate both sides. On the left, 1 over y times dy dx. On the right, we have a product rule, x and the natural log of cosine x. It might help you if you put parentheses around that cosine x. Then you'll see that that cosine is on the inside of the natural log. And when we do this derivative, again, product rule, first x times the derivative of the second. And the derivative of the natural log of cosine x is 1 over cosine x times the derivative of cosine, which is negative sine x, times, you want to go one step further, times the derivative of the inside of the cosine, that's 1, plus, right, that was first derivative of the second, plus the second, ln cosine x times derivative of the first, which is 1. All right, cleaning this up a bit then, simplifying. We have 1 over y dy dx equals, all right, what happens here? Negative x sine x over cosine x plus the natural log of cosine x. And I think I would do another step of simplifying here and look at this sine over cosine and make that a tangent. So we have 1 over y dy dx equals negative x tangent x plus the natural log of cosine x. All right. Now multiply back for solve for dy dx. So we're going to pull that y over. So dy dx is y times negative x tangent x plus the natural log of cosine x. And then sub back for the y, which was originally cosine x to the x. So dy dx is cosine x to the x times negative x tangent x plus the natural log of cosine x. Whew. And there we go. There's your derivative. All right. One more thing to talk about here, and I kind of put this cloud over here, and I didn't mention it initially because I didn't want to mess around with it, but I needed to deal with this right here. We have to talk about why this restricted domain is on here. Why does cosine inside of here or why does x actually have to be between 0 and pi over 2? I need you to remember back to your pre-calculus. With natural logs. Do you remember that you can't take the natural log of a negative number? And it's not just natural log, it's any log. We can't take the log of a negative number okay, by restricting the domain here, we guarantee that cosine x to the x is a positive number. And if you think for x between 0 and pi over 2, right in here, cosine's positive. So we have a positive number to a positive number, that quantity is positive. So we guarantee that cosine x to the x is a positive number, and then it is mathematically legal to take the natural log of both sides. Because it's not mathematically valid to take the natural log of a negative number. So we have to guarantee that by doing this natural log of both sides, we are in fact doing the natural log of a positive number. So that's why this restriction was put on there. All right, thank you very much.